Greetings and welcome, friends. Today we are talking about solving systems of equations, which you might be like, wait a minute, we talked about this yesterday. And you're right. There are multiple techniques of doing the same kind of problem, each of them having their own efficiencies, methodologies which may perform better in certain situations than others. So today we're talking about elimination. You might recall yesterday we were talking about substitution, and substitution had it was very strong when one of our variables had a positive or negative 1 for the coefficient of one of its variables. Elimination deals with the situations when that's not the case rather effectively. All right, so elimination can be a little bit better than that. But first of all, I just want to talk about a couple things, some terminology. First of all, a system of equations is a set of two or more equations. We've talked about that before, right? A solution is a point of intersection of the graph of the equation. So graphically speaking, if I had two equations, something like this and like this, right, the solution is the point of intersection between those two, right? So that would be the solution, right? There we go. That arrow is a little bit off, but that'll count. It's good enough. So the solution is the point of intersection, or the values of x and y that simultaneously make each equation true. Now there's a couple of descriptive words that I just want to talk about to describe these. The word consistent, all right, it describes a system that has at least one solution. At least one solution. Okay, all right, that's not bad. The word inconsistent. Inconceivable. Now I'm writing inconceivable. No. What am I doing? Inconsistent. There we are. It's not necessarily the well, I guess it is the opposite of this. Yeah. A system with no solutions. No, I'm not spelling things today very well, but that's quite all right. I wonder if you can get a degree in college on spelling. Like instead of like, 19th century British poetry, like you're like, I'm just going to get a degree in spelling English. That'd be pretty great. All right, another word that we need to know is dependent. Ready for this? A system with infinitely many solutions. Infinitely many solutions. And then the fourth concept is independent, which describes a system with exactly one solution. Okay, so here's 4 terms. And what I want to point out is the following. Notice that, let's see, consistent has at least one solution. Okay, so this little picture I drew here a moment ago has one solution. Okay, inconsistent has no solutions. What would that look like graphically?
Parallel lines.
Yeah, 2 parallel lines. I'll draw a little image over here. So imagine 2 lines that are parallel, never crossing, would have no point in common, right? Let's see, dependent is a system with infinitely many solutions. What would that look like? Oh. Yeah, 2 lines that are exactly the same. You might use the word coincident. They exist simultaneously, right? So there's infinitely many solutions there, but I want to point out that not all combinations of x and y would work in this case. Only the points that are actually on the line, right? Like here's a point that wouldn't work in that system, even though there's infinitely many solutions. Okay. Now, question: is a dependent system consistent or inconsistent? Right? Infinitely many is at least one, so dependent is also consistent. Right? It's inclusive of that. It's a subset of the consistent case of numbers of solutions of systems. Right? Let's see. Independent is a system with exactly one solution. All right, so that's the one that we kind of described earlier, where it's just plain old intersection of two lines crossing at a single point. Makes sense. And question, is an independent system consistent or inconsistent? Also consistent. And I guess arguably, well, we're talking about a system of linear equations here, so we're only ever going to have one solution or infinitely many. I can't have like two lines cross at only 2 points, but that would be like some gray area between dependent and independent. But anyways, so that's the idea behind some of these terms, this terminology that I want you to be aware of. Now, so that applies to all systems, okay? Not just ones that are solved by elimination, but also ones that can be solved by substitution. And technically, I mean, I've been drawing all these pictures here for a little while now. Technically, systems can be solved graphically. If you graph them accurately, you might be able to find the point at which they cross. But graphing is very inefficient because it's not very accurate. And also, like, what happens if my point they cross at is at, like, 1,000, 5,027? Like, I don't want to have to draw a grid that would somehow be able to measure that. So it's not very good at long range, I'd say. Or if my solutions were like crazy fractions or something, graphing would not necessarily help me answer that question. So let's talk about, let's do a little recall first. Recall. Before I get into solving by elimination. All right, let's say I wanted to add the following. Add the following. If I want to add 2/3 plus 5/7. Okay? Do you guys have any thoughts as to how that would be possible without just getting the decimal equivalents or approximates on a calculator and plugging it in? What would I do? How could I add those fractions?
2/3, 7/7.
Ooh.
And 5/7, 5/3.
Okay, now Connell is working towards the direction. He was actually trying to accomplish a least common denominator, and he was in the process of doing that, but I just want to fill the rest of us in. The LCD between these two denominators is 21. All right, it's the smallest number that both 3 and 7 go into. And Connell realized that he wanted to multiply each of these fractions, top and bottom, by the part of the LCD it was missing. Right, so this one was 7/7, and this one was 3/3. Right, and that would end up giving us the 14/21 plus the 15/21. Right, and then I'd be able to add those and get the 29/21. Right, wonderful, wonderful. However, let's consider one other problem real quick. All right, what if I had, and I'm not even going to take this one the whole way. What if I wanted to figure out 5/8, plus 3/12. Now you might think this skill is completely unrelated to solving by elimination, but there's a common skill set between this and elimination that would be helpful for us. What is the LCD between these? Let's see, 24? Yes, I agree. Notice that 24 is not just the product of 8 and 12, which it was in the case, right? The LCD did happen to be the product of the previous one, because those were what's called relatively prime to one another, but don't worry about that right now. So what would I multiply this one by? Top and bottom, to get 24 in the denominator. 3/3, and this one by 2/2, right? And I'd be able to go from there. So the ability to kind of recognize what I'd multiply each of these by in order to get a same number, that's the skill that's going to be helpful when solving systems by elimination. So let's actually talk about this. Solve Solving by elimination method. Okay. So I'm going to give you the steps first, just because that might be helpful. And then we'll actually do a couple little examples on it. So step one for elimination, I'm even going to write this in white here. Step one is line them up. So line up like terms in columns. All right, so that means that if I have my x's, my y's, my equal signs, my constants, both of my equations should have those lined up in columns. Okay, and it doesn't necessarily have to be x, y equal constant. It could be y equals x constant, or any sort of thing, as long as your equations are in agreement with each other. Oftentimes, step one will already be done for us. Step two, this is the key one that's quite interesting. We multiply one or both of the equations by a number, or numbers, I guess, if it's both, resulting in opposite coefficients. For one of the variables. Very wordy, but very specific. All right, and this step is the one that's actually really similar to getting an LCD between two fractions. That's why I wanted us to recall that skill, because if I can build off of your previous knowledge, this concept will actually come easier to us. Here's step three, is add them up. Add the equations and solve. Well, add the equations, thereby eliminating one of the variables because they had opposite coefficients. And solve for the remaining one. Okay, all right. This is interesting, perhaps. A little different technique, but we actually don't care. Notice we're not looking for one of our coefficients to have already had a positive or negative one leading coefficient, right? It doesn't matter to us. In step four, we substitute this answer the solution into, and check this, into any of the equations. Usually I plug it into one of the original equations, but it doesn't matter. So yeah, remember when solving by substitution, we had to always plug the revised equation into the one we did not originally solve for. Not the case here, doesn't matter, doesn't matter. And 5, last but not least, is check, which we won't always do that, but I want to at least explain how that works. You would substitute the solution into both equations. The original ones specifically, ensuring that it works for both of them. So, lots of words there, 5 steps. Step 2 is the big one. Sometimes step 1 and 2 will already be done for us, which is quite nice when that happens. But yeah, let's see. I imagine you guys are just finishing up. Okay, and if not, you can always go back to the video. So here we go. Let's do 2 quick examples. We'll be done. Here we go. Solve. And specifically, I guess we're solving by elimination. Solve the equations, the system, 2x plus 3y equals 7, and negative 4x minus 5y equals 13. Aha. So step 1 said to line up the like terms in columns. Notice I've got my x's all together, my y's together, my equal signs, my constants. Step 1 is done. We're good. We're good. Now step 2 was the tricky one. What was the words? It was multiply one or both of the equations by a number resulting in opposite coefficients for one of the variables. So let's take a look at this. Take a look at these x's. All right. What would the quote-unquote LCD between 2 and 4 have been? 4, right? The smallest number that both of those go into is 4. All right, so if I wanted opposite x's, I would probably get a 4x here and a negative 4x, and they'd be opposite. I'm not committing to that just yet, but that's what it would have been. What about for the y's? Between 3 and 5, what's the smallest number those both go into? 15. So if I have a choice, which one should I go for? Opposite x's or opposite y's? Mathematically, it doesn't matter. But preferentially, I like smaller numbers better, right? So let's go for this 4 on the x's. So what do? I have to now multiply one or both of these equations by a number giving me my opposite coefficients. So what could I multiply the top equation to give me a 4x? Multiply the whole thing by 2. And what do I have to multiply the bottom equation to get a negative 4x? Well, it's already got it. So that's why, in this case, I only have to multiply the top. Right? And I want opposite coefficients, so for instance, if both of them were going to be positive, I would just make one of those a negative or something like that, just to make sure it all worked out. So let's do that. So 2 times 2x is 4x, 2 times 3y is plus 6y, 2 times 7, don't forget to multiply the right-hand side here. Oftentimes students do. 2 times 7 is 14. And now notice, behold, I have opposite coefficients. Hooray! Which is helpful for step 3, in which I add these equations together. So add them up, just vertically. And all the corresponding parts are all lined up already from step 1. I've got opposite coefficients, so let's just add these. Negative 4x plus 4x becomes nothing, 0, right? Which is perfect. This is why it's called the elimination method, because I just eliminated one of the variables. So let's see, the x's cancel out. Negative 5y plus 6y is how many y's? 1y. 1y. Mago y. And 13 plus 14 is 27. So I've just solved for one of my variables, and how do I solve for the other one?
Plug it into either one of the equations.
Yeah, plug it into either of the originals or any of the equations. I like the first one better because 2, 3, and 7, they're smaller numbers. Right, that's all. That's all I'm doing. So 2x plus 3 times 27 equals 7. Let's see, 2x plus, let's see, 60 plus 21, 81. If I'm doing this right, equals 7. And now I'm just solving for x. Right, so notice, actually, yeah, let's point that out first of all. Notice no fractions occurred. None. I eliminated one of the variables. That's great. I mean, the answer still could have fractions in it. I can't avoid that if that's the case, but the process didn't have fractions showing up, which is quite appreciated. So let's see, what's this going to be? Negative 74, if I'm not mistaken. And then divide both sides by 2. And we get x is equal to, what's that, negative 37? I believe so. So I end up getting my solution, avoiding the fractions in the process. So the elimination method is quite nice at dealing with these types of situations. When I, don't have any ones for my coefficients anywhere. Now, on tonight's homework, you're going to be doing elimination method for the whole thing. So even if there was a positive 1 coefficient, still commit to using elimination just to see how it behaves. Sometimes those work out quite nice. So let's look at one last example. Let's solve the following. What if I've got 5x minus 8y equals 2 and 4x plus 12y equals 20? So, for the x's, what would the coefficient I'm shooting for be? 5 and 4 both go into 20, right? And I'm not committing to that just yet, but we'll see. 8 and 12, what do those both go into? I think we had that question earlier. 24. So I'm going to go for the 20 here. But what I want to point out is if I was going for the 24, notice I'd have to actually multiply both equations by something in order for that to happen. Okay? So that can occur. Oh, actually, it looks like I'm going to have to do that for the 20s as well. What am I doing? Silly me. So what do I multiply 5 by in order to get 20? 4. And what do I multiply 4 by to get 20? 5. But I want opposite coefficients, so it doesn't matter which one, but one of these I'll have to make negative. I could, make the top one negative if I wanted, something like that. So let's do that. So 4 times 5x is 20x. 4 times negative 8y is negative 32y equals 4 times 2 is 8. Negative 5 times 4x is negative 20x minus 5 times 12, 50, plus 5 times 2 is 10, so 60 y. And negative 5 times 20, I believe, is negative a hundo. Wow, look at this. Would you look at that, though, guys? Would you look at it? Wow. We've got opposite coefficients. Add them up. 20x and negative 20x. Bam! Those just like kill each other in a knife fight. Negative 32y and negative 60y is negative 92y equals negative 92. Aha. Divide both sides. Oh, this is looking real nice. Here we go. Here, that box was a little bit too close to the one. I needed some better margins on my framing. Where do I want to plug this one to find x?
5x minus 8y equals 2.
Why do you like that one, Jacob?
I like it because it gets me notice kidding because it has smaller numbers.
Yeah. Those are your favorite numbers? Yeah, and we could practically do this math with our eyes closed. With half our brain tied behind our back. Hopefully it's not the logical side of our brain. Yeah. Well, I believe we only use 10% of our brains at a single time. Although we use more than 10% over like a whole day. Right, if you're doing different activities and stuff. But nonetheless, anyways.
How can you stimulate your brain the most?
Telling stories, remembering the past, drawing pictures, all sorts of different things. So 2-1 is our solution. Not that bad, guys. The whole key, notice the similarity. That's why I had us do the recall of adding fractions, was that kind of LCD-ish concept will be the most helpful there for you. So thanks for watching, friends. TNN un día más bien del mundo.